Alright, in this lesson, what we're looking at here is energy from the atom. So nuclear fission is one of the more common ones, and there are many countries around the world that use nuclear fission to produce heat to then produce their electricity from. Alright, so there's three videos there about nuclear fission, splitting the atom for beginners, nuclear fission, and then chain reaction. Mouse trap and ping pong balls, should have a look at those, particularly the mouse trap and ping pong balls. Gives a good idea of what chain reaction, or which we'll talk about later. Alright, so one of the people who looked at this was Henri Curie and a guy named Frederick Joule, and they bombarded aluminium with alpha particles, and then after that they had the first fission reaction, and then another one further down the track was Enrico Fermi, and he made a study of nuclear reactions, and then he bombarded, so they used an alpha, and Fermi used neutrons, and that's the one we look at today when we're talking about nuclear fission. So this was, in the 1930s was when this was going on. Alright, so I mentioned about nuclear reactors, and so Otto Hahn and Fritz Strassmann, and then there's a lady named Lise Meitner, Otto Frisch, and they're all mentioned in your notes. So what they were confirmed was that there could be a capture of a neutron by a nucleus, and then that led on to a disintegration of the nucleus after that. Alright, so as we know, nuclear stability depends on the balance between the protons and the neutrons in the nucleus. So by shooting a neutron in there and it capturing, you would get disintegration. And so that's what nuclear fission is all about. Alright, so in our nuclear reactor, what do we do? Alright, so here's in the nuclear reactor, what happens. So the equation's up the top, and here's a diagram. So what happens here is that we fire a neutron into a uranium-235. That then becomes uranium-236, which is unstable. And rather than as nuclear radiation and decay in that sense, by doing this, it's actually made the nucleus so unstable that what ends up happening is that it splits up into a couple of components, so a couple of different atoms, and then gives off more neutrons. So we've then got 3 neutrons. So this particular one, we get krypton and barium, and 3 extra neutrons. Alright, so those neutrons could then interact, and we'll get to that. So there's another equation as well. Alright, so here's another option. So krypton and barium, but also tin and molybdenum could be also another one. So again, same thing in terms of neutron fired into uranium, gets caught, becomes unstable, splits up, and this time you get 5 neutrons. Now, the key thing that makes this so interesting in terms of what people are after is this bit on the end, this energy. And a lot of that is heat energy. And that's what makes it so attractive, because what we do is we get much more than coal. So much more than coal or fossil fuel. Much more than fossil fuels. Right, and so that's what makes nuclear fission in terms of generating power. So that's what makes it so attractive. Products that it has, not necessarily so great, because they're radioactive and that causes issues with themselves, but simply in terms of the amount of energy we get out, very attractive. Alright, so in general what happens is that you have a neutron, you fire it into uranium's typical 235, you get out two other elements. We get fast moving neutrons, and also you get energy, and it's typically 200 mega electron volts of heat energy. Now, that may not seem overly, exciting, mega electron volts, because it's still, in terms of things, quite small. However, what you've got to keep in mind is this is for one reaction of one atom. And so because you've got billions and billions and billions of atoms, you need to multiply that by billions and billions and billions. All right, so they use countries that use the energy to make steam, and then steam to do their turbines. All right, so in terms of, I said it was more than fossil fuels, so the amount of energy we get out of this is about 20 times that of normal radioactive decay. And hundreds of times more than fossil fuels. Alright. Alright, now you can't do it with just anything. There's only certain things that can do it. Alright, so now let's move on to this. So we've got these fast moving neutrons. And so that's what leads to a chain reaction, because those fast moving neutrons that are coming off, there's a few things that could happen. Right, so here's your notes, and the gaps in your notes, see the red there, you can fill those in. So 4 things could happen to these neutrons. So first of all, we could get capture by the uranium, but no fission. Captured by another material in the uranium ore, so it's not going to be pure uranium, there'll be other stuff. Could escape altogether, because so it could get out of the uranium ore altogether. Or it could be captured by another nuclei and further fission. And so this last one here, that's the one that we're interested in, because then that sets up the possibility of a chain. And so this diagram shows that. So first of all, we have our neutron captured by uranium-235 splits, and now we get 2 neutrons. And so then that could split with a couple of different uranium atoms, and we get more neutrons, and so on and so on. And so it could keep getting more and more and more. And that's kind of what that video, the ping pong balls and mouse traps, is showing. Alright, so more and more get produced, increasing the chance of fission. But there's a thing that's called critical mass. And that's simply the same. So if you have a small mass of uranium, then it's very easy for your neutrons to get out. However, if you have a large bit, then a neutron produced in the middle here, it's got to get past a whole bunch of stuff before it can get out. So it's more likely that in the second scenario here, where the larger mass, that you're going to get capture and further fission occurring. All right. Now, of course, the downside of that is just having a big bunch of stuff is that you can get a huge amount of energy in one place, and then you have a nuclear explosion, i.e. a nuclear bomb. So what in power stations, what they do is they have these rods that go into the uranium, and these rods serve to capture the neutrons, and so the rate of reaction or chain reaction can be controlled somewhat with that. All right, we talked about I mentioned before about the energy, so right, it's the energy that release that we are interested in, energy release. Right, that's what we're interested in. And so there's a couple of videos, energy mass equivalence and the real meaning of E equals mc squared. So Einstein, he's the man in a lot of ways. A lot of our modern physics relates to stuff that he did. So he got a Nobel Prize in 1921 for his work on stuff, but he's done a lot of stuff, not just with nuclear energy. But he came up with the whole idea of energy mass equivalence. And so he said that energy equals the mass times the speed of light squared. So what he said is that there could be perhaps some mass being turned into energy in some way. All right, there's a little physics joke for you. You matter until you multiply yourself by the speed of light, then you energy. All right. Now, all right. So all that laughter. Let's have a look at a typical reaction. Let's have a look at the reaction where we got a neutron firing into uranium, and it splits up, and you get barium, krypton, 3 neutrons, and then some energy. And so this energy, what we're going to have a look. So in your notes, it talks about atomic mass units. So one atomic mass unit is the mass of one proton, and so that saves us. And so 1U is equivalent to 1.66, and there's a whole bunch of by 10 to the minus 27 kilograms. All right, so that saves us having to worry about, if we're talking atomic mass units, worrying about numbers with extremely small numbers with powers of 10. There is an equivalence for mega electron volts, the speed of light, and that equivalence is 931.494 mega electron volts per speed of light squared. All right, there's a standard, of course, carbon-12 in terms of the atomic mass unit, and the proton, it's carbon-12 is the standard. All right, let's have a look. So before fission, so that's this one here on the this side there. So before our neutron, and in my notes on the website, so 1 neutron, and you've got to go to lots of decimal places here for this stuff. All right, so it's that in terms of atomic mass units, the uranium. So the uranium-235, again, this is in my notes on the website. So there's that, and then so the total amount of mass, when you add those up, 236.052588 atomic mass units. Alright, so this is the one we're interested in. So that's before. Now after fission, when we have a look at after fission, we've got a few things. We've got neutrons. And in this particular one, we've got 3 neutrons. So the 3 neutrons, 3.025997 atomic mass units. We've got some barium, 141, and so that's 140.9, 144064 atomic mass units. We've got the krypton, 92, which is 91.9261528 atomic mass units, and so that gives us a total of 235.86655539 atomic mass units. So I said the totals, what we're interested in. When you have a look, there's a difference in the totals. So what is the difference in the totals? Alright, so the mass loss. Is the 236.05258 minus the 235.866, I should say, 8665539, which when you work that out is not much. It's 0.1860 341 atomic mass units. And now when you convert that, and in the notes on the website is the calculation showing you what I've done, but you get 3.089171102 by 10 to the negative 28 kilograms, which is not much, but too many. And if we use E equals mc squared, and we say that the mass then is dropped by that much there, 3.0809171102 by 10 to the minus 28 kilograms, and we multiply that by the speed of light, which is 3 by 10 to the 8, and square it, you end up with, as I said, this 2.78025391 by 10 to the minus 11 joule. Alright, and as we know, 1 electron volt is 1.6 by 10 to the minus 19 joule. The calculation is in the notes. And when you do that, that is energy of approximately, so you can look at the calculation what I've done there, but 172 mega electron volts. Alright, so mega electron volts out of one little tiny piece of mass loss. So that challenges our normal thinking in that there can, be a mass difference. Alright, however, it does explain, and explains very well, where that energy comes from. Alright, I mentioned before about nuclear energy, so there's consequences. Alright, because our products are radioactive, and so we've got to do something with them. Alright, so if our products are radioactive, got to do something with them. There's also, and so one of those is nuclear weapons, or even not just nuclear weapons, but like it's happened in Chernobyl and in Japan and a couple other places with power stations, there's a shock wave. Alright, so shock wave from the explosion, so it's just this energy. It can be, you know, air particles, all sorts of stuff being pushed out, shock waves, so that can do something. There's the fallout, so with the explosion, so you know, as we know, when anything explodes, you get dirt and stuff all being flinged out everywhere. So you can get nuclear radioactive particles flinging out everywhere. And the other thing that is a problem is the heat, so there's a huge amount of heat, so it burns things. Alright, so there's a couple of examples there, strontium-90 in your notes as to what that does. Alright, also, even if it's peaceful use, as I said, products radioactive, what are we going to do with them? How do we store them? And the like. Alright, so that's it for those. So if you've got questions, make sure you ask. Watch those videos, they're quite good. And then there's questions in your text.